My name is Aisha Batul and my roll number is 16TE01. In the previous lecture we have studied about the discrete Fourier transform, and today we will move on to the fast Fourier transform. In the discrete Fourier transform we have the biggest disadvantage, that is its computational cost is quite high. This can be found by if we have n components then the number of additions that we get from the discrete Fourier transforms are n into n minus 1, and the number of multiplications that we get are n cross n, that is n square, which is a non-linear function. So in order to compensate this disadvantage, we move towards the fast Fourier transform. The main formula for fast Fourier transform can be derived as, let us suppose the w of n equals to e raised power minus j 2 pi of n. Putting into the previous formula of discrete Fourier transform, we can get x of k as n equals to 0 to n minus 1, x of n to w of n k n. Okay, we will use this formula in our today's calculations. Now let us have a unit circle that is divided into 8 parts for n equals to 8. It's 0 degrees, it's 180. Okay, n of 8 0, n of 8 1, n of 8 2, n of 8 3, and similarly okay, here we have plus 1 and minus 1, similarly minus j and plus j, and here .7071 plus j 0.7071, and here it will be minus 0.7071 minus plus j 0.7071, and it will have both the negative values here as it is in the third quadrant. Okay. In the previous lecture I have considered a sequence x of n as 1, minus 2, 3, 1, 2, minus 1, 2 and 1. I write it as time domain and the frequency domain separately. X of 1, x of 0, x of 1, x of 2, x of 3, up to x of 7. Its values are and the frequency domains. Similarly, I got the following values. You can find it in my previous lecture. Index of 7. Okay. It will be minus 2929 plus j 1.7071, and x of 4 will be 9, and x of 5 will be the conjugate of x of 3, and x of 6 will be the conjugate of x of 2, and x of 7 will be the conjugate of x of 1. Now if we move to the fast Fourier transform, we divide this into odd and even components. Let's suppose we divide it into the 4-point discrete Fourier transform. It will have the even inputs and it will give 4 even outputs. Okay, and similarly I will divide it into the 4-point discrete Fourier transform odd. It will take the odd inputs here and will give the odd outputs. 1 0 2 3, and similarly here x of 0, x of 2, x of 4 and x of 6, the even values. There are 1 3 2 2, and here I will get the values for even sequence, and x of 1, x of 3, x of 5 and x of 7. Okay. Now I will use the previous formula for x n is equals to 0 to 3 and x of n to w n k n. Okay, now here w k n is equals to 4. Let's suppose I am calculating it for 4 2. Okay, I will divide this unit circle into 4 parts here. It's 4 0, 4 1, 4 2 and 4 3. It will have the values and -1. Okay, I'll calculate only the one value. Let's suppose that I'm calculating E1. It will be, I'm putting these values here, 2 0, x of 1 2 4 2 1 plus x of 2 2 4 2 and x of 3 4. Okay, I will get the following results. 4 and 2 are -3 plus okay, and the final result that I'll get it -1 minus. You can calculate the rest of the results by using the same formula. Okay, this will be -1 minus j and -2, and e of 3 will be the conjugate of e of -1. Similarly, odd sequence will have the following results, and it is basically the conjugate of e of 1. Okay. We can see that the computational cost in the case of discrete Fourier transform, we had the additions and multiplications. Additions were 56 and the multiplications were 64. But now in the fast Fourier transform, we have the additions 12 plus 8 equals to 32, and the multiplications were also the same. So these have been decreased. That's why we prefer fast Fourier transform over discrete Fourier transform in order to compensate the computational cost. Okay, for moving fast Fourier transform to the discrete Fourier transform, we can use the formula E of n plus w of n k to 0 of n. Let's suppose that I am calculating x of 1. I can put the values here, 8 1, and I can get the result. You can put these values from the unit circle that I have drawn before. I hope that this lecture will be useful to you. Thank you so much.